This video is still part of section 4.2 and deals with finding the area under a curve, but in this one I'll be addressing upper and lower sums. The idea of an upper sum is that it's also known as circumscribed rectangles, but the idea is that you're going to approximate the area that's under the curve by creating rectangles that have endpoints on the function. So as you can see here, the upper sum is marked in red and has rectangle endpoints on the right side, whereas the lower sum has rectangle endpoints on the left side. These are just used for more of approximations. They're still within the interval a to b, and it's still used to find the area that's underneath this curve. But as you can see, the upper sum is going to be a little bit greater than the actual area, and the lower sum is going to be a little bit less than the actual area. So the formula for the basic upper and lower sums is right here, where you've got the sigma notation again, and then you have f of xi times the change in x. Now, that if I look back at this picture, the f of xi is going to correspond to how high the rectangle is. Remember that these down here are all some sort of x value. So think of I represents what rectangle it is. So say you are taking f of x sub I. That means that you'd be taking the area, or f of x sub I would correspond to the y value of this rectangle right here, whereas f of x sub 2 would correspond to the height of this rectangle right here. The delta x just represents change in x, so that's going to be in this instance, we're going to have all of the rectangles be the same width. So that's just going to be, say this was like 1/4, and then this one was 1/4, 1/4, 1/4, 1/4. So that's not going to change. As you can see here, the change in x is going to equal b minus a over n, b being your rightmost, your farthest to the right interval, what's the word, restriction, and then a being your leftmost one. If you think of it this way, this symbol means the sum of so many rectangles, where n corresponds to rectangles. F of x sub I represents the height of a certain rectangle. I meaning whether it's the first, second, third, etc. rectangle, and then change of x represents the base of, and this should be rectangle, not triangle. So here's an example. Find the upper and lower sums for a region bounded by f of x equals x squared and the x-axis between x equals 0 and x equals 2. Now, if you were to see a picture of this, it would look like this right here, where once again red corresponds to the upper sum and blue corresponds to the lower sum. We're first going to find the upper sum, just because it's the easier one, and then you'll see why. So our formula is I equals 1 down there, and then our number of rectangles, we're going to set it at n. This is just an arbitrary number of rectangles. F of xi times change in x. Now our change in x is going to equal b minus a over n, which in this case our rightmost is 2 and our leftmost is 0. So 2 minus 0 over n equals 2 over n. So 2 over n. Now what we're going to do for what we'll be inputting into the function is we're going to take our change in x, because that represents the x value, and we're going to multiply it by I, because that I is going to represent the particular, that I is going to represent which rectangle we're taking the height of. So it's like when I equals 1, that means we're taking the area of the first rectangle, which means that it'll be f of 2 over n, and that will be the height of our first rectangle. And then, so now that we have that, if we plug this back into our original f of x, f of 2i over n is going to equal 2i over n squared times 2n. All I did there was just plug in our input as x into our original equation. Do some simplifying, and we get 4i squared over n squared times 2 over n. Can simplify even more so that we get 8i squared over n to the third. And now if you can recognize from the last video, we have n's and i's and a summation. So our goal is to keep our i's on the right side of the summation and then get our n's to the left side. So in this case, I'll move it up here. I can factor out a 1 over n to the third and times it by 8i squared. If you multiply those across, then you get the same thing as down here. Move this over to the front, so you get 1 over n to the third summation 8i squared. This constant, 8, we can even bring that out to the front now to isolate our I squared. So now we have 8 over n to the third summation of I squared. I'll just move it over one more. And then move back up here one more time. It gets a little bit cramped, but 8 over n to the third. If you can recall from our summation formulas, I squared corresponds to n times n plus 1 times 2n plus 1 all over 6. Can cancel some of these things out. Becomes, yeah. So now distribute a little bit. 8 over n squared times 2n squared plus n plus 2n, so that's plus 3n plus 1 all over 6. Multiply across. Well, can actually simplify that down to 4/3. Multiply across and you get 8n squared plus 12n plus 4 all over 3n squared. Let's put a limit in front of that. Now that we've got that limit in front of it, since they have the same number, same raised both to the same power, it's just a ratio of the coefficients. So our answer is 8/3. Oops. As for the, now that was the upper sum. So now for the lower sum, it's a little bit more confusing, but it's all the same idea. First thing we're going to do is just solve for our change in x. That's going to be the same, 2 minus 0 over n. So that's just 2 over n. Now, in this case, when we're trying to find out what our input variable is going to be, we're going to have to consider what is going on with the graph. So as you can see, if we were to take the if we were to use the x value of if we wanted to get this area of the first x value of this first rectangle, then we wouldn't be using this height right here, because that's that doesn't that reaches all the way up to right here on the function. What we want to get is the height right on the left side of the rectangle. So in order to do that, we're going to have to change around our input a little bit, and it's actually going to be same thing right there, but it's going to be f of 2I over n, so the same thing as with the upper sum. However, we're going to have to subtract a 2 over n, just a single factor of the change in x, so that we can get that height that we need it to be at. Whenever you have a left endpoint as height, you're going to have to subtract one factor of change in x. Notice how right here the height of the rectangle is, you're looking for it on the graph, it's on the left side. Whereas if you're taking the upper sum, the red, then, like say we were taking this sum right here. For the red, the thing is on the right side. I actually have to continue this video into a second one.